Hello everyone, my name is Samba and I'm here to present my group. So the topic of our project is scope and variable. But as we can probably see, these are broad concepts. So we're just gonna restrict ourselves a little bit and talk about this concept in a manner that will fit our need, which is discrete mathematics. After talking about this, we decided to introduce a few concepts that will help us understand scopes and variables. But these are words that you're going to be hearing throughout this presentation. And they overlap with this project. I mean, after all, they all intertwine. But we understand also we have to walk a fine line because we do not want to overlap with other projects. But keep in mind that every word you hear, you're going to be hearing will be explained thoroughly, and you will walk out of this presentation with a clear understanding of everything we talked about. Just on a final note, we can just say that some of the concept a few group members will talk about. This is going to be brief, and that's usually an introduction of something that another member will talk about later. All right, now to introduce the next speaker, Brendan.
Hey there, I'm Brendan Fahey and I'm here to talk about domain and quantifiers. Alright, now to start off, we'll talk about a variable. What a variable is a value that represents a number that can vary, typically as an input or output. Now then, where this typically comes into play is in a domain. Now what's a domain, you ask? Domain in the context of logic is the set of data for which a statement's truth value is assessed. Now, why is domain important? Let us say that p of x is the statement 1 divided by x. If you make the claim that p of x is greater than 0, that statement would be false. Because if you took 0 or negative 1, that would make the statement false. However, if you change p of x is greater than 0 when x is greater than 0, now this statement is true. Because for all values greater than 0, 1 divided by x is greater than 0. Thus, the domain can significantly affect the truth value of a given statement. Now, the universal quantifier is denoted by the symbol above, and its definition is p of x for all values of x in the domain. Now, to put that plainly, statement p of x is always true for the domain. You could also say that the statement is true until at least one value of x in the domain is false, to help you understand that concept. Similarly, existential is defined as there exists an element x in domain such that p of x. Now to put that one plainly, at least one value of x makes p of x true in a given domain. Or you could also reword that to the statement is false until at least one value of x in the domain is true. Using those couple of tricks, you can make sure you keep existential and universal aligned. Now, here to talk about scope is Diana.
Okay, hi everyone, I'm Diana, and I'm here to talk about scope. So hopefully by now you're all very familiar with this definition. So basically, scope is just a part of a logical expression to which a quantifier is applied. We have a simple example here. So there exists an x, x plus y is equal to 0. So in this case, x plus y equals 0 is the scope of the existential quantifier here. And x is within the scope and y is outside the scope. And here we have more complicated examples. Like this one, it's pretty long, I'm not going to read it. Or this one. So for these examples, it's kind of hard to tell at the first glance, like which is the scope of which. But so I want to introduce syntactic tree, which is not in the textbook, to you guys, so that this is a way of visualizing the long expression like this one. So I'm not going to go into details about like what is the definition of this syntactic tree or how to draw it exactly, like step by step, but it's pretty straightforward and self-explanatory. So you simply just separate the expression and into branches. So maybe we're not gonna worry about this very last level, but you can see here. So the existential quantifier for x and this predicate r of x are under the same branch. So in this case, x in r of x is within the scope of this existential quantifier. And for this p of x, you don't find any simple quantifier here, so we're gonna go up a little bit. In this branch, we can see there's a universal quantifier here. So the x in p of x is actually within the scope of this universal quantifier. So just to make sure when you use this syntactic tree to visualize things, you want to look at the same variable in the predicate and also the quantifier. So say if we have more than one variable here, say we have x and y, maybe we have a p of x and y here, but since the quantifier is only for x, so this y here may not be in the scope of this quantifier. And that's my part.
Hi everyone, I'm Mingming Jia and I'm here to talk about bound and free variables. A bound variable is a variable that is within the scope of a quantifier. For example, in the statement, for all x, q of x is bound by the universal quantification, all of x. A free variable is a variable that is not within the scope of a quantifier, nor is it assigned to a particular value. In the statement, for some x, q of x implies p of y is a free as it is not bound by the existential quantifier for some x. Here are some practice examples on distinguishing bound and free variables. Let's determine how many variables are bound and free in this statement. So when we look at the premise, we see that quantifiers are for some x and for all y. So this means that x and y are bound while z is free. In the conclusion, we see that for all of z, x plus y equals 2. But here, z does not appear in the scope, so both x and y are free. And it's that or z equals 2. And z is not bound by any quantifier. So this gives us 2 bound variables and 4 free variables. Now let's look at the importance of applying scope when the order of quantifiers differ. So as we see from this example, both statements have the same apply the same scope. However, the two mean very different things. The first statement, for some x, all of y, x plus y equals 0, means that there is just one x such that for any number y, the sum of x and y would be 0. This is false because if that one x were to be 1, the only y that would add to be 0 would be negative 1. But this statement says that any y would work, and that is not true. The second statement says that for all y, some x, x plus y equals 0. This statement is true because it states that for any number y, there will be an x so that the sum of the two would be 0. So if y were negative 1, then x could be 1 and it would be 0. If y were 2, x would be negative 2 and that's also 0. So the two examples have the same scope, but the order of the quantifiers can change the meaning. So thank you for your time, and we hope that we were able to help explain variables and scope.